Hey guys, this is going to be the last set of notes in Unit 1. So we are going to have our unit test at the end of next week. It'll include all notes we've done and this set of notes. So next week we'll spend some time just practicing. All right, so we're going to start out with our function transformations by just beginning with a basic function. So what we're going to do is we're going to look at how these functions change when you change the equation of the function. So let's say f of x is just x squared. All right, makes it easy. It's just a basic quadratic. Over here, let's just sketch a picture of what x squared looks like. X squared is a totally symmetrical parabola. It's symmetrical about the y-axis, like that. All right, and you could graph it if you wanted to. Plug in a 1, you get a 1. You plug in a 2, you get a 4. Plug in a 3, you get a 9. Plug in a 4, you get a 16, right? This is what your x squared function looks like. So what we're going to do is we're going to start with that function, and for each of these transformations that we make, we're going to start with this and show how it changes when you make the changes that are in each of these equations. All right, so what I'd like you to do is start off by just sketching this in each of these boxes here. Okay. All right, so obviously those aren't perfect sketches, but those are your x squared functions, so we're going to start with each of those when we show what changes in each one of these examples. Okay, so here's what I'm going to do. Let's say, for example, a equals 3. All right, let's do that. And let's say that I take my x squared function and I add 3. What's going to happen to this function is I'm going to take this whole thing and I'm going to shift it up 3 units. And that doesn't change no matter what the 3 is. That's just going to control how it goes up. So if it's a 5, it's going to go up 5 units. If it's a 10, it's going to go up 10 units. If it's a negative 10, it's going to go down 10 units. So this number on the end that's added to the end of the function controls a vertical shift. So let's sketch a picture of our function up here. All that's happened is it's gone shifted upward, and the distance that it's shifted by is a. It's shifted up a units. Now if we take the same function and let's say f of x then equals x plus 3 squared, and that plus 3 is inside of the function. Notice over here this says x plus a. That's because we're adding the number inside the function. That's going to control a horizontal shift instead. So a good thing to make a note of here, this would be a vertical shift. This would be horizontal. The interesting thing about a horizontal shift, though, is that when I add 3, it's actually going to send my function 3 to the left. And if I subtracted 3, it would send my function 3 to the right. So the way that we're going to note that here is I'm going to draw a parabola that's over here like this, because I added a, and that distance is going to be negative a, right? Because I'm adding a number, but for some reason I'm going backwards. And if you graph it by making a table, you'll see that you have that effect. Let's go to f of negative x. So let's say f of x was just negative x squared. Actually, on our f of x function that we've got here, this x squared function, it wouldn't look any different. You can just draw the function right over the top of it. And that's just because that's this function. Because what adding a negative inside the parentheses does, if you change the function itself, is it's a reflection over the y-axis. So you can see here why that would have no effect, right? This is symmetrical already over the y-axis. So if I reflect it, it'll look exactly the same. Some functions won't, but in this case, it looks exactly the same because it's just a reflection over the y-axis. And if I were to add the negative in front of the function, so for our negative f of x, let's say f of x was negative x squared. Now that negative is not inside the function, it's outside the function. That's going to be a reflection still, but it's over the x-axis. So that would look something like this. because it's been reflected with that negative. All right, so these are important notes to make. These are the very first function transformations we're going to do, and you're going to do more of them on Monday. There are 2 more we have to talk about. Okay. Down at the bottom, I've given a new function. It's a square root function, negative the square root of x minus 4 minus 2, and we're going to graph it. All right, to graph this, it's going to be easiest if we draw our axes. This is where our y-axis should go. That'll make the graph easiest for us. I just know that because I've graphed it. And then our x-axis, and we can put our x-axis right here. Okay, and then we're just going to graph g of x. So g of x is a function we've never seen before. So the easiest way to graph it then would just be to make a table. So let's say we have our x values, we have our g of x values. The easiest number I think to try first when graphing a function I've never seen before is 0. So let's just see what would happen if I plugged in a 0. I don't want you to write this down. But if we were to do g of 0, we would have negative the square root of 0 minus 4 minus 2. Okay, so that would give us negative the square root of negative 4 minus 2. This is an issue. We can't have that, right? We can't take the square root of a negative number. So because we don't know how to do that, we can't use 0 first. The function does not exist at 0, at least not here on this real number line. All right, so we've got to find a number that will give us an actual real result. I think the best number to start with then would be 4, because I would be able to subtract 4 and not have a negative number under the radical. So let's see what happens when I find g of 4. G of 4 is negative the square root of 4 minus 4 minus 2. That would give you negative the square root of 0 minus 2, which would be negative 2. Okay? Good. I'd encourage you now to take the reins and graph the rest of this function on your own. Plot 4 more points. Okay, so it looks like 5, 8, and 13 will also give us some good numbers. If I plug in a 5, then I'm doing 5 minus 4, and taking the square root of 1 is pretty easy. If I do 8, then I'm doing 8 minus 4, taking the square root of 4 is pretty easy. If I do 13, I'm doing 13 minus 4, taking the square root of 9 is pretty easy. So I'm giving myself numbers that are going to make this an easy thing to graph. And now I can just plot these points. So I've got the point 4, negative 2, that's right there. I've got the point 5, negative 3, that's right there. 7, 8, negative 4, 9, 10, 11, 12, 13, negative 5. The interesting thing about this function, and we're going to do more with it in class, but I can't just go forever with this. For example, I can only start the function there, and we do know that I could just keep plugging in larger numbers and it would keep giving me values. But one thing we can't do is we can't put any numbers this direction. We can't assume that the function exists there, because it definitely does not. Remember, we figured that out when we were trying to graph f of 0. It didn't exist at 0, and it doesn't exist at a lot of those points. So this function stops right there at x equals 4 and does not ever continue in this direction any further, because, as we know from plotting numbers into our equation, that would give us negative numbers under the radical, so the function doesn't exist over there, and it just stops right there, but does go forever in this direction. So when we get to class, we're going to work more with this function. Otherwise, hopefully this is making a little sense to you, and we will practice some more of it on Monday.